Welcome. This is the first video with pre-class tutorials for Math111Z at 2 o'clock at OSU in fall 2023. The week 3 feedback indicated that a number of students are asking for more lecture to help them prepare to be successful in the workbook. And since I don't want to use our class period to take away workbook time, I am adding these lectures to Canvas so you can watch them before we do the sections in the workbook to give you a sense of how to do the problems. These are completely optional. The idea is for them to be helpful. I'm not doing a complete lecture. What I will be doing is going through each workbook section and using similar problems and occasionally writing definitions or explaining concepts, but really just giving you a framework that you can watch and watch again and watch slowly if you need to, so you have an idea of what you're getting into with the workbook for that section. So we've already started section 4.1 in class, but I will go through parts of 4.1 as well to give you some information. Okay, so let's start on page 82 with the summary of x-intercepts and y-intercepts from an equation. Okay, so x-intercepts are when the function is 0. So let me take a function, for example, x times x minus 3 squared times x plus 1. So if I want to find the x-intercepts, I want to find when the function is 0. So I put 0 underneath the function, and I solve for one or more values of x. In this case, if x is 0, then that becomes 0. These terms aren't 0, but I don't care, because anything times 0 is 0. If x is 3, then you have 3 in front, and then you have 3 minus 3, and you have some other stuff. So that is 0. The output is 0. And if x is -1, then this term is 0, and you get 0. So the x-intercepts are when the function is 0 and solve for x. As another example, so there's my answer. Here's another example, g of x equals the cube root of x plus 7. Okay, well, I need my output to be 0. You could do this in two ways. You could say, let me cube both sides, and then I'll get rid of the cube. 0 cubed is still 0. I get x plus 7 should be 0, so x should be minus 7. That's the algebraic way. Or you could look at this function and say, the cube root of x plus 7 is 0 when x plus 7 is 0. Because the only way to get 0 from a cube root is to get cube root of 0. It's 0. And you also get x equals minus 7. So that's how you get the x-intercepts. You set your function equal to 0 and you solve for one or more x's. Y-intercepts are found by plugging x equals 0 into the function. So let's look at each of these functions. So if I have f of x equals x times x minus 3 squared times x plus 1, I'm going to do f of 0. That doesn't mean the output is 0, it means the input is 0. So that's 0 times 0 minus 3 squared times 0 plus 1, which is 0 times 9 times 1, which is 0. I'll do two more. Right, so in this case, setting x equal to 0 also gave me 0. So my y-intercept is 0, 0. Like a g of x I want, so that's cube root of x plus 7. I want g of 0, which is cube root of 0 plus 7, which is cube root of 7, and I'm satisfied with that answer. I can find out the decimal approximation, but I don't feel the need to. Do one more polynomial, let's say. Let's do x plus 4 squared times x minus 1 times x plus 2. So if I want h of 0, I have 0 plus 4 squared times 0 minus 1 times 0 plus 2. 4 squared is 16 times negative 1 times 2, so that's negative 32. That's how you find the y-intercepts. And zero product property is a fancy name for 0 times anything is 0. So if I have this really big, long, complicated polynomial, x times x minus 3 squared times, let's add some more terms in there, x plus 4 cubed times x minus 5 to the 7th times x plus 3 squared. And I want to know when my output is 0. I just need to make sure that one of these terms is 0. Because as long as one of those terms is 0, the whole product is 0. So my zeros are x equals 0, x equals minus 3, or sorry, x equals positive 3, should be a positive, x equals minus 4, x equals positive 5, and x equals minus 3. That's the zero product property. This comes up in polynomials and rational functions. All right. Moving right along, let's look at domain of functions. So if I have a rational function, f of x equals 3 over x minus 2 and x plus 3. I use a different number here to avoid confusion, x plus 4. The domain of a rational function, the easiest way to find this is find the problem values, i.e., when the denominator equals 0, and that happens when x equals 2 and when x equals negative 4. Because if x equals 2, I've got a 0. 0 times anything is 0. Now I'm dividing by 0, which we can't do. Same thing if x equals minus 4. Other than those two problem values, everything else is okay. So the domain is find the problem values where the denominator equals 0 and exclude them. So if I'm going to exclude them, I can go all the way down toward negative infinity. I can come up to negative 4, but I have to cut negative 4 out. And I can go up to 2, but I have to cut 2 out, and then I can go up to infinity. I call this cutting it out, where you go up to negative 4, open parentheses, and then start at negative 4 with an open parentheses. That's rational functions. Let's look at logs. So we expect you to know a basic log function like log of x. We expect you to be able to do a basic graph of log of x. We expect you to know that there is a vertical asymptote at x equals 0, and that this point is 1, 0 on a basic log function. So we expect you to know that the domain of a log function is not including 0 and going up towards infinity. So the domain of a log function is any positive number. So now if I have a different log, like log of x plus 3, I know that what goes into my log has to be a positive number, which is just saying that in this case, x plus 3 has to be positive. So x has to be greater than -3. I'll do another one. Here's a real tricky one. Log of 4 minus x. Okay. Rather than thinking about transformations, don't think about transformations for this. Just say that piece in there had better be greater than 0. So this time I'm going to add x to both sides. I'm going to say 4 has to be greater than x. So in this case, my domain only gets up to 4 and can go down towards -infinity. Where in this case, my domain starts at -3 and goes up to +infinity. Moving on. If I have a rational function, sorry, a radical function, like the square root of x plus 4, it just helps to remember in a square root, what goes under the square root has to be greater than 0. So x has to be greater than -4. So my domain, sorry, start over. When I make mistakes, because I do that, so you just have to deal with it. I can also be equal to 0, because 0 can go into a square root function. So x has to be greater than or equal to -4. So that's my domain there. And if I have another rational function that looks like 13 minus x, I want to remind myself that 13 minus x has to be greater than or equal to 0. So I'm going to add x to both sides. So 13 has to be greater than or equal to x. So 13 is the largest possible value for x, but it can go as small as I want it to. All right, that kind of covers a summary as well. So I'm not going to write that in there. I want to notice this radical function had an even root, like a square root. But if I have a function h of x is a cube root, I want to ask myself, what does that have to be? Well, with a cube root, you can be any number. So this really means x minus 2 can be any number. So that means x can be any number. So my domain is all real numbers. But if I have a fourth root, I think, okay, so fourth roots, I can't take the fourth root of a negative number. So once again, this x minus 2 has to be greater than or equal to 0. So x minus 2 has to be greater than or equal to 2. So my domain starts at 2 and goes out towards infinity. Last piece from this section, piecewise functions and domains. The key to a piecewise is look at each piece separately first, and then put it together. So I'm going to make up my own piecewise function. If I have a function that looks like x minus 3, when 0 is less than x, less than or equal to x, less than 4, and x squared plus 1, if I better be careful. X minus, let's just do this. I'm making this up, so I might make mistakes. If x is 4, then x minus 3 is 1. So I can do x squared if x is greater than or equal to 1, for example. I can even do that if I say they're equal on both sides because they agree. Because if x is 4, x minus 3 is 1. And if x is 1, x squared is 1. So this graph actually, it happens to look like this. Looks kind of like that. And now my domain, the easiest way to do it is say, what's the domain of this? 0 up to 4. What's the domain of this? 1 up to, oh, I made an error. So skip over this video, or this part of the video. Let's start another part. Go back to piecewise. Use my function f of x, x minus 3, 0 less than equal to x, less than equal to 4. And I'm going to do let's just do x squared. I'm going to start at 4. And I'm going to start strictly greater than 4, just to save myself the headache. Because when I was doing the other one, I made a mistake. So scratch that on your mind and look at just this one. This graph looks like 0 less than equal to 4. And then there's a hole there and it goes up like that until you get to 7. But that's still a function, so that's okay. And then in my domain is 0 up to 4 and also 4 up to 7. And I can write it like this, that's totally fine. But notice there's a 4 there and a 4 there, and that one's a square bracket. So it really covers everything between 0 and 7. End of video.